Roger once again, Mud Fossil University, with by far the hardest thing I have ever had to try to explain all in one short video. And what I am going to explain is the nature of light, the nature of energy, the nature of the particle of light, the spin of light, the different forms of light, including the light that we see and the light that we don't see, and the light that is stationary as static electricity. It is all the same thing. It is all the same particle. And these are the experiments that Rod Warren and I did years ago, and I've been studying them for years. And I think I have an explanation now as to how the actual particle works. Now, I can't tell you exactly the nature of the internal energy of the particle, but I can tell you what I see occurring, and I can account for the energy. And I can talk about what CERN asks for. We see it in our experiments. The Higgs bosons. We see light accelerated. We see the right-hand spin. We see the actual physical particle of light. We see the spin of the, well, I didn't do pictures of the galaxy, obviously, but the galaxy rips itself through the ether that is in front of it, because there's all kinds of particles there. It's not, we're spinning through that. It's nothing. It's not like there's nothing there. Obviously, it's there. That is what's heating us up. Nothing here is being understood, and it's being worked around simply to accommodate Einstein, who was wrong, and I'm sorry he was wrong. Case closed. Now I'm going to show you why he was wrong. At Fossil University, today is the 24th of January 2019, and today I'm trying to figure out a way to articulate how light actually works. Oh, no, light is light. Well, no, it's not just light. And heat is not just heat, and cold is not just cold. All these things, everybody's, oh, I know how that works. Well, if you think about it for a couple seconds, if I say to you, how does heat work and how does cold work? If I take this rock right here, all right, that's cold in my hand. If that was 400 degrees, I wouldn't have known that. I would have picked that up, would have burned my hand. Now, what's the difference if it's 400 degrees or if it's 70 degrees? What's the difference? Same rock. If it's 400 degrees, it'll end up being 70 degrees. You won't know the difference. It comes right back to this. Why is that hot when it's hot? What is the mechanism that causes this to be hot? And they're going to say, well, it's excited electrons, or excited molecules, and they're jumping around over it. I agree with that. Why are they jumping around? Well, in the heat, what made them jump around? What is the heat causing this to jump around? Where'd it come from? Well, it's come from sunlight. It comes from your stove when you turn on your stove, and it burns, and then the heat comes up. And well, what is the heat? What's the heat made out of? How does the heat get into there? What is that mechanism? I want to know the mechanism. I don't want to know all the words. It's just it's entropy, it's enthalpy, it's this, it's all kind of different little words that mean very little until you understand the process that word is supposed to represent. And nobody understands the process. They understand the words, but they don't know. They can't get the process in their mind. We're working with these right here. That right there, that is the thing that does every single thing there is relating to energy in our realm. All right, these are electrons, and they're the particles that are in space that are thrown from the sun when it is excited, because it is scrubbing through the ether. I have shown this in these diagrams and so forth, and the structure of the galaxy forces everything to spin rapidly through that debris that was ahead of it. That's spitting out light. It's spitting out debris of all kinds. We are too. So we have to get through that. When our planet and our solar system scrubs through that mess of ether, it heats up. Well, the heating up is what? It's forcing electrons into other electrons regions. That is what's going on. It's a crushing of electrons into other electrons regions. I'm going to show you that right now. Then we're going to go into the details of how that crushing actually affects that little tiny particle. And it all relates to the right-hand rule. And here's the right-hand rule. It means if the electricity is going that direction, zip, the field will generate going this direction and following the particle. And here's what I show as a representation of it. Now, I got this idea from a guy named Stan Tenen, and I'm going to show you his research. There's the particle. Zip! These are a shell surrounding it of negative particles that are thrown away into an exact circle surrounding that particle as it goes forward. They call that the boson particle, which, of course, when they talk about bosons and Higgs fields, it's in highly accelerated particles, which we did. We highly accelerated, and we show the bosons, we show the Higgs fields. And these are the Higgs fields that surround the cascading particle, which is called a boson, in accelerated particles, which we accelerated. In a regular light particle, it's just a regular light particle, and it doesn't have these fields surrounding. The fields only show up for an instant as they crash into the unrestricted medium. So let's go look at the experiments. Now we're going to go into the experiments. Now, like I said, this is the hardest thing I've ever had to do, and I've been working on this a long time. I got a couple little Wile E. Coyote diagrams to show you about what I think is going on with light, and I did have a eureka moment, and we will be going through all of that. And what I'll go through all of this sort of briefly, what I think is going on, and why I say these things. So let's start off with the experiments. Now, up here you see that there's a whole series of things going on, and I'm going to start from where light is just the light from a red laser to where it becomes accelerated into a Venturi. And looking down at the output of the Venturi, we end up with that mess. It's highly excited energetic particles. And then exiting the Venturi, we end up with this, which is, I believe those are Higgs bosons. They're highly accelerated particles coming out into unaccelerated space and crashing. Exactly what they're looking for. And as a matter of fact, CERN has the same pictures. They don't have the actual events like we do, I don't think, but they have pictures, and they were looking for this, and all they have to do is call us. We got it. Now, this shows the right-hand spin. This shows the particle coming out of the accelerator, slowing down, and displaying itself as an actual particle. And that is absolutely fascinating. You see that particle? That's the particle. And it is a torus, I believe. And that's why I'm showing all these little things and what I think is going on. How did we get positive and negative energy here? Why is that? How's that possible? That's a piece of light. That is a particle of light. It came out of the light through the accelerator, and now they're coming out through here. As they slow down, they display for 2 instances. Now, let's look at the rest of the stuff, and we'll take it one at a time, and I'll try to explain exactly every interaction that I'm talking about. And I think I understand now what light really is, how it works, and where it collects. And it is the actual free electrons. They don't have to move. Light doesn't move sometimes. It sits around. Static electricity, same as electricity comes through the lightning. Same as the electrons that come from outer space, from the sun and from stars. They come and shoot out from all of those excited sources. And eventually they collide with something. It's as simple as that. When they collide with something, they squish this torus. And in the neck of the torus, it creates a tremendous Venturi effect, which is what I am going to explain right now. So, as I said, this is light just being shot out of a red laser. That's the wave front of it. And there's literally only a tiny little bitty beam of particles in the center. They are actually particles. You'll see them in a second. And all of this like glowy little bits here. That is what happens as light. This is the free electrons that are in the air that are being concussed. Those are the kind of things that collect on you as static electricity and can create paths for lightning and so forth to go through the air. As light smashes into it, they concuss and poof, they glow. Now let's look at what happens in the next instance here. So that was light straight from the from the regular red laser, pulse red laser. Now this is that same wave of light, and you can see that little tiny line of dots. That is what laser light is. Not all this, not all that. It has nothing to do with that. It's this. Now, why is this wave sucked here? Well, I can tell you why it's sucked in there. That's sucked into a Venturi. And a Venturi does exactly the same thing as a waterfall. Or as a hose, a nozzle in a hose. Everybody's going, floating down the river, everything's fine. All of a sudden they start going faster and faster and faster. What's going on? They are accelerating. Why are they accelerating? This is pulling them downstream. And the harder you get, the faster you go. And the harder you get, the faster you go. And then all of a sudden you're over the edge and the case is closed for you. Now, this is a crushing effect of all these particles, because these particles aren't just sitting out there and have no excess region to themselves. These particles contain just a tiny little dot, and they want to own a good sized region. You see how much of a wave they create coming through the atmosphere? Coming through the, these electrons are sitting out here just having a nice time, and all of a sudden this little dot comes through there, and it is tough enough to make that huge wave that we saw a minute ago, and now it's being pulled through the Venturi, and as that tiny particle that owns a region, it's tiny in the center, owns a big region, whoosh, coming through there, it now, all of its buddies are waiting for it, and they're pushing each other, they're slamming, they're bashing, and they're turning white. And now they're displaying, and now they're crushing against each other. And now all of a sudden they hit that Venturi, and it's explosion time. Coming out the other side, you get the interference patterns through the Venturi, which is nothing more than a slit experiment. Same thing as a split, except it's formed in a shape that forces the electrons to crush into like two airplane wings against each other, metal pins. There's nothing more than construction nails, actually. And because they have to force into that region, now they don't want to be there, and they turn white, and they turn into plasma. Everybody's touching each other, do not want to be against each other. They all want to be apart, and they blow away like this in lines. And that is what creates this. Now, these particles, for some reason, are negatively, well, when I say negatively, they have a charge to them that exceeds, one charge exceeds the other. And I'm saying it's negative charge. So the negative charge exceeds the positive charge. Let's call it that way. And it could be the other way around. I don't know. I'm going to call it negative because negative indicates it's less and positive indicates it's more. So I'm going to say that the negative charge has, see, it's confusing, but let me put it this way. Going into here, you have a lot of current because it's coming through here at, let's say 100 miles an hour. I mean, obviously it's not that, but let's say it's coming in here 100 miles an hour. Well, when it reaches here, it might be going 1,000 miles an hour. So it's 10 times faster. What does that mean? It's got 10 times as much voltage. So the voltage creates this huge reverse wave. You see these little tiny lines out here? Little tiny things. They don't do that much. These are the kind of waves here that do the damage. Damage, I say. They do the pushing hard, hard, hard. The ones coming back, they have a lot of voltage. They go way out, but they're not like a big sledgehammer. They're like a ping pong ball, but it goes way out. And this is like coming in with you know, a shot put or something, like a 20-pounder, and going back with something that weighs an ounce. But they go way back. Bing! It goes way back. You go bloop, it goes just back this far. That's what's going on here. Now, how that affects the interplay between the Venturi in and the Venturi back out, I believe it is the inductive reactance. And I'll try to explain that again. This is kind of, like I said, this is not easy to explain. So, what are we taking away from this inductive reactance? In other words, you induce a current, a big, huge reverse field, because I crush these fields into just a big glob of fields, and they're pushing back like this, and they're creating all this backflow. Now, what's getting caught in the middle is these little tiny dots. What are those little tiny dots? That's ether. Those are electrons. Those are electrons. They could be light. If they were moving like this was, they'd be light. If they were coming from the sun, as sunlight, the same particles are light. If they were going through a wire as electricity, same particles are. So, what's the difference? Nothing. Nothing at all. These can be, they will move around. They'll go all over the place. They'll attach, they'll detach, they'll attach to you if you're dry, or if you're wet and it wants to find moisture and the air is dry. That is the nature electrons move. They are the things in life that do everything. They are the movers and the shakers. Okay, so now we got light, we got accelerated light, we got plasma, we got electrons invading other electrons' regions, creating huge reverse electromagnetic fields that show us there's ether everywhere. So now, what happens at the Venturi? This happens right here. This is chaos. Now, when I say chaos, when they come out, they are so accelerated, they're just like in plasma, really, because they don't want to touch each other. They hate each other. They come out and they start to turn into yellow, which indicates that they are losing energy. Now, why are they losing energy? They're losing energy because the restriction in the Venturi creates a less dense space. The restriction creates a flow that atomizes the particles that move through it because it accelerates them, and it therefore creating less density. The less density lets these things accelerate. When they accelerate and they finally come out into the more dense, they smash into that. It's called the Higgs boson effect, where radiation comes in at a high speed, and neutrinos and so forth they call them, and they crash into a medium that is less dense. I'll show you all this stuff shortly. So now we've seen light, accelerated, chaos. What comes out of the chaos? What does it turn into when it slows down? It turns into Higgs bosons. And before I show you what our Higgs bosons are, I'm going to show you what CERN would like to see for Higgs bosons. A simulated, not the real thing, they don't even have the real thing, Higgs event at LHC, Large Hadron Collider. The large collider there, they have a Hadron Collider. Now, there's the particles, they want to smash them together. They're hitting particle to particle. They're using heavy particles. We're using the lightest of all particles, electrons. They're using proton particles, the cores. So they, bam, they run this one this way and this one this way, and they explode them together, and they see what happens. Well, I think they need to look now with mud fossil eyes and say, if this was nothing more, well, this is my eureka moment. I need to talk about that later. But if I know what's in the core now, I think, according to my theory. And if I'm right, they may see exactly what I'm suspecting they will see, and we'll talk about that later. But right now, I see exactly what they want to see, because I think the particles that they're looking for are very, very similar to the particles that I am looking for. So that's that picture. So that's their simulated picture. That's what they want to see. Well, guess what we have for them? We got the real thing. Now, right there, as you can see, is just exactly what they were looking for. Here's the smash. Only for us, it's a Venturi that accelerates it. We're not smashing something into something else. We're just accelerating our particles and letting them smash into unaccelerated space, which is denser. As they slow in speed, the charged particle, which is what they call a boson, it comes through accelerated, called Cherenkov radiation. I'm going to go through this and show you what they say about this very shortly. It's exactly what we have. The Cherenkov comes through here. It's highly accelerated white light. You see the little tiny filaments? You see those little filaments? Excuse me. On every one of these filaments is a Higgs field. The filaments are bosons. They're charged particles. So what does that mean? That particle has a charge on it. It's spinning through space, and everything that surrounds it is being pushed away in a nice, elegant little cylindrical pattern as that little tiny particle goes. You don't see the particle. It's too small to see. It's in the center there. All you're seeing is the effect of it spinning and the negativeness of it forcing the other particles that surround everything in the atmosphere to turn into little circular fields around it. Now, we see there's all different colored fields here. That means there's different frequencies. Now, they're all going to turn back to red, which is very, very, very interesting, because that means they came from a red source. They can change colors, and then they will end up going back to a red source. Now, why don't they stay purple? Why don't they stay orange? Why don't they stay magenta? I think I understand. And I'll try to explain it. And it's strictly the matter of that now they are not moving at the speed of their normal movement when they come out of that red laser. They are now going through a faster speed, but that will change in a second or two, well, instantly. You only get 2 waves of this, and then they turn back into their normal. Well, they pretty much stabilize at that point. But I'm going to show that. You'll see it. Now, something else that I want you to see. So first of all, you understand that's the Cherenkov. These are the filaments called boson charged particle carriers, meaning they carry a field with them. This is the Higgs field. Now, that one there, that one is of particular interest. You notice how all these have fields. That doesn't have a field. You see it comes sweeping out of here this way? Sweeping. And it's really brilliant white. Why is that? Why? Well, I looked at that for a long time. And I think it's spinning backwards. And the reason I think that is because it's gathering. It's supposed to spin to the right-hand spin. And then they make all these other ones get out of the way to the right-hand spin. Right. And I'm going to try to explain that on some of my Wile E. Coyote drawings over here. But as this one's coming out, this was coming out with a left-hand spin. You know, they're supposed to come with a right-hand spin. This was coming out with a left-hand spin. And I believe that puppy there is gathering the electrons into itself and glowing as a response. Now, so what? Who cares about that? Well, maybe I care about it. Maybe you care about it. Maybe somebody that cares about antimatter cares about it, because that could be antimatter. You say, oh, you got all this stuff. Yeah, well, we got all this stuff. What do you want me to say? It's here. Well, what do you think it is? What do you think it is? Why is that glowing white and all the rest of them don't? Why is that? My explanation is that it is spinning backwards, just as Venus spins backwards. It has no magnetic fields. It gathers all of that energy into itself. It's 900 degrees on the surface temperature. Venus gathers all the electrons because it spins backwards, scrubbing as hard as it can possibly scrub into the oncoming electrons, which are everywhere. So I'm saying that's spinning backwards. The definition of antimatter is the same particle with an opposite charge. That's it. Same mass, same particle, came from the same source, red laser. And I'm saying these will all turn back to red. So I'm saying that's the same size particle as all the rest of them. They didn't spit out one big white one. So that has the same origin as everything here. So that's spinning backwards. It's gathering the electrons to itself instead of spinning to the right and pushing them away into a field. This is as much as I can get to. I mean, this is deep. So anyway, I hope you understood that, because it makes sense to me. Because you see all these little dots, that's what it is. It's just spinning to the right, and it's push, 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 and they push them all the way to. But this one's gathering them. It says, come here, come here, come here, come here, gather them in. Anyway, what is the end? This result? What does that thing do? Does that explode like a time bomb? Well, guess what happens? Very interesting, my friend. Let's go back here. So. Here we go. Boom. That's done. Well, here's what happened when it hit the deck. And what deck are we talking about? We're talking about another one of these disks. Each one of these is, I'm saying, is a light particle. It's a light particle. You call it anything you want. It's an energy field. I'm going to call it a particle because I see a particle when I get down to the dark white, dark white. Now, you'll see that shortly. So, bang, boom, right in here. What's that all about? And what is that about? This I have no explanation for, except that if this is reverse, is antimatter, and that little darkness next to it, and that little darkness next to it is like a suction of fields or something. I don't know what it got. You know, somebody else is going to have to look at this. Let's put it that way. All right, so let's. I don't know what that's doing. It just happens. It's there. What can I say? And you know, that's the only time I've ever seen it. So there's that. Now. Why do I say light spins to the right? This is why. And I can say right here why it accelerates. It is spread apart here and it is compacted here. It's obviously slowing down. It's spinning to the right. That means it will drift to the left. So it is spinning to the right. It is slowing down. This is the length before it turns into the Higgs fields. So this would be the boson section. Boom, Higgs fields. Let's see what we got. Well, I think I showed you the Higgs field. Okay, so this is a nice Higgs field. This is coming out at us. That's the particle. That's the field following that particle. It's diminishing in intensity because it is now in an area where the molecules and electrons in the environment is coming through now oppose it. They oppose it. It says, I'm coming through. I say, whoa, whoa, whoa. And they say, well, I'm coming through. And he says, okay, you can come through, but we're going to stop you. And they and it gets, see, power, power, power. And you can see it coming right out. This is all a spin, you know. This is not like boom, bada, boom, bada, boom, bada, boom. I think it's all one big gigantic spin, which is what you would expect. And each one of these little dots is really the particle. You know, the other electron being stimulated as it passes them. So it's a very, very... I see no other possibility for the things I'm saying. So now we saw that. So now here it is coming out of the accelerator. The green goes way out before it crushes into the ether because it's more powerful than the red. See, there they are right there. It's coming out and it's slowing down. This one here, soon that will, you see how much more white that is than that? I think it gets, as it really hits and slows, it really brightens up. That's what it appears to be. See how bright it gets like that? Now, where are we? Okay, now what do we got here? Woo-hoo-hoo. This is a cloud chamber experiment. Now, what they did, and of course I didn't do this, but I follow all these things, but I'm seeing something here that absolutely blew my mind. Now, if you've watched this, if you follow this thing around, I mean, it's a there's a track in here with a track in the center of it. There's like a field separation and a track in the center. Now, what are we seeing in this field? Well, how did they get this? Way up above here at the top, there's what they call a Van de Graaff generator electron pulse. All right, so here's what happens. It sits up way up here, say 10 inches off of the plate, which is here. Of course, it's flat on the ground. And under that plate, there's a metal receiver that wants to receive the pulse. So the Van de Graaff generator, which generates a huge voltage, thousands and thousands, hundreds of thousands of volts. And it's just, you know what I'm saying? It discharges. That is the point of discharge. When it does that, this is exactly what happens at that instant. I mean, you're seeing even these things, these black dots and so forth. I don't know. I can't account for every little detail here, but I'm telling you what I'm seeing here is a structure, an atomic structure. Now, what the gases they have in here are usually alcohol, vapors, something very, very, very cold. And that's what you're seeing is that cold vapor being energized, really, being vaporized, and then displaying some kind of energy pattern within it. So there's a lot to look at that. I mean, every single one of these things is not just oh, look at that, that's nice. No, I study these things I could study that for a year and find something still every single day I look at it. I'm telling you, I find things every day. Like even this here, I'm looking at that and I'm thinking, ooh, that's interesting. Anyway, let's keep going. But I think it comes in here. You see it? Look, it comes in here. It goes around. And if you follow this around, it goes around and around and around. And it ends up going somewhere in here, just tapering off in the center. And this is your S1 orbital area. And then the rest here is your rule of 8 area. I'm telling you, that's what I see. Okay, so now we saw that. Now let's look at the particle, the red particle coming out from the accelerator. I told you the green goes further out. The red crashes pretty quick. Now, what are we seeing here? Here's the particle. And here's your spikes coming out. I say that's a torus. I think it's a torus. It's obviously got power and no power. So let's look at my little diagrams and see if it makes any sense what my interpretation of what we see. So don't forget, the scenario is light, which was just laser light coming into a Venturi, highly accelerated, coming out of a Venturi in plasma, settling down for 2 cycles and then turning back into its red normal laser light. Or it'll be red anyway. I don't know if it's end up being laser. Well, it sure looks like it at the end. But anyway, it'll end up being red light at the end, and as it started. So why is all these things happening? Let's take a look at that. All right, you saw what the Higgs fields I showed look like, and I believe these are the Higgs fields. And they call them electron neutrino showers. So your power coming in, your high voltage particle coming in, which is coming out of the accelerator, extremely high voltage, smashes into the atmosphere, creates this smash to the atmosphere, and creates all these cones. So this is the Cherenkov, highly accelerated, correct, I'm right, thank you. The Cherenkov radiation from the electron shower, produced by an electron neutrino, they call it that, I call it accelerated electron, produces multiple cones. I go along with that. I agree, you guys are right. The ones you want to remember: regular light, accelerated light showing all the things I talked about, Higgs bosons, whatever that is. Then you got this, which shows the electron. I believe that's the electron, dark and white, and with the spikes going up and down. I think it's going through a torus. And then, of course, the thing. So now let's go into my description of what I think we see. Now, as you saw in the light, I believe were the electrons. It had a light and a dark and a light and a dark, and spikes coming up and spikes coming down. One side was light, the other was dark. Now, I believe that's the result of the interaction of the crushing of the energy, whatever that energy is. As this is, the right-hand rule is the law in physics. Everything spins to the right, and that is their natural intention, and it's the least resistive way for it to spin. Now, when things spin to the right, when I'm coming up from here, and I'm spinning to the right, like this, around and around and around and around and around to this pinch point. I can't go any further. I cannot get to the other side. I know you think, oh, it's just going to go through. No, it won't, because these are electrons. Now, think of this. Remember how they turned white when they got close to each other. Here they are out in this big bubble. They're having a nice time. And all of a sudden, they come up here and they start getting closer and closer. They get whiter and whiter. Remember, we saw it. And then all of a sudden, they start glowing like crazy. And they're going down in the right-hand rule. They hit bottom. And they say, that's it, boys. You're out of here. And woof, it goes backwards, but it's still spinning to the right. Now watch this time. Remember, it came in this way, to the right, spun around just like the penny you put in the little arcade thing. It hit the bottom, still spinning to the right. This time, it comes back out, and it comes back out this way. But it's dark because it's going still spinning to the right, but it's going backwards. It's supposed to only go this direction, spinning to the right. So now it's going backwards, still spinning to the right. It comes up here, it's dark. Now it gets over to here and it starts to get sucked back in. It starts glowing as they get crushed more and more. It's spinning to the right, around and around and around. Snap. Ah! It spins to the right still. And now it's gathering itself because it's going backwards. The electrons are being pulled into themselves. And out it comes, and it's dark until it hits here. And then it starts to get... It gets sucked back in, around, poop. And it keeps going to the right, and it sucks itself back together, and then it starts backwards. So you get the light and the dark, the light and the dark, and the spikes going up, the spikes going up. Now, let's look at it on my little diagrams. Okay, so now, where are we? I say the Venturi accelerates. We know that's a fact. Now, I also know that the architecture of that Venturi, the width of the Venturi, the roundness of the pins, will change the output. It changes the Venturi's output. The width of that changes the frequency and the resonance. So the length of the frequency that's allowed will change. Now, our absorption lines and our emission lines, they're both exact frequencies. So, is it due to the size of the Venturi? Yes, I say it is. What does that mean? It means that there's 8 extremely stable Venturi sizes, and there are possibly 9. So I say those, and I know that because I can see them in the vibration of salt. And I have sewn up and probably show it. This is running long, I know, but that's the way life is when you want to learn this stuff. Now, so I'm saying those are the main Fraunhofer lines. There's 8 of them, and they are related to the S1 and the rule of 8 lines. Those are the stable frequencies, and they're the dark lines that Fraunhofer found first, and those are the absorption and emission lines. They will a molecule will absorb it if it's cold, exactly that frequency, and only that frequency, and it will emit that same exact frequency if it is too hot. It's got to be the Venturi. It's got to be the Venturi size, and the Venturi size dictates the size of the actual electron. I say there's 8 or 9 species of electrons. That's all I come up with now. And then I'm going on about some other things here that don't concern you. They're about music and light and sound and how I think they actually communicate, to be perfectly honest with you. I've gone into that and I'll go about it more. But when you take this torus, what you have is a crystal. It's a crystal. I don't care how you look at it. It's a crystal. If that's the light is the plus, and dark is the minus, and light is the plus, and dark is the minus, and you've got a spike coming up here and a spike coming up there, you've got a crystal. You've got a crystal. I don't care what you say. It's a crystal. Now, I don't know what it's made of. It's a form of a crystal. It looks like a crystal. It acts like a crystal. It has the polarities of a crystal. To me, that's a crystal. So, what does that mean? When here's the way I see this right-hand rule working. We saw a dipole of just dark and white, but I really believe what's actually happening is this is actually spacing way out. Because remember we saw in the Venturi experiments the reverse EMF was huge. The reverse electromagnetic fields, as it came through the Venturi, it sprayed in the back all that white stuff, very, very dense white. But this way, it made an enormous reverse field, and I believe that's what's happening here. So it's being pulled in really hard, and they're coalescing. They're getting dense and light as hell. And I mean, no, not light. They're compacting, and they're giving off light because they're crushing into each other's regions. Right-hand spin, in. Dead stop, right-hand spin back out. Get away, or crush itself in, whatever. But they're huge, and they're dark because they're way out into fields. And then they start to coalesce again as they begin to get sucked into the Venturi and dragged back in, just as we saw in the experiments. I mean, the Venturi sucks it in, it speeds it up, it makes it glow, it makes it turn white. And it's still turning to the right, but this time it's going backwards. So it's gathering instead of displacing. It comes back out, and then it's still spinning to the right, and it comes back around. Now it gets sucked back in again, and it just keeps doing this. Now, will this do this forever? No, absolutely not. You sit here and just do nothing whatsoever, and you will have no anything here, but you will own a region. If I come up and smash it, it'll start going, it'll do that. It won't do it forever. It'll just go for a couple seconds, and then it'll settle down again, unless more stuff comes and keeps slapping at it. More light comes from the sun. Bam, 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 bam. This thing's going to be jiggling like this. It's going to be hot. It's going to be glowing. We're going to have light. We're going to have heat. If I keep smashing, obviously it's going to glow. If I sit it out of the shade, it's going to cool down. Simple as that. And now, so, I mean, it's not simple, but it's not that hard either. Now, the same force travels right-hand around the torus in and back out from the inductance at the Venturis. All right, so we went over that. Now, what else here? Let's see. Well, here's something about nukes. No, that's here. All right. Nuclear reactions destroy the resonance stability. So they destroyed stability within the crystals in the cores. And they force an unstable union with resonance frequencies that don't settle. They just won't settle down with each other. They're just always on the edge of breaking. And when they do, if they break a single little electron out of there, it's not going to really hurt anybody. But if they break a chunk out, which is like a bar magnet, and like a half a dozen electrons attached to a half a dozen other particles, heavy particles, it's going to hurt somebody. So anyway, I think most natural molecules are stable. I know uranium, they say, is a natural molecule, and who knows. Now, then there's stuff about mild steel. At 1420, it loses its magnetism, 1420 degrees, and it gains it back at 500 degrees and gets it back. Therefore, crystals settle as the electrons leave. It's obvious the electrons are forced in there. Once they get out of there, at a certain point, the crystals reestablish themselves. Now, the same thing happens is with superconductivity and those floating magnets. When they get down to like 200 and whatever it is, 200, let's say 220 degrees, I have no idea what temperature, but say minus 220 degrees, all of a sudden it goes, bloop, pops right up in the air. That means there's not enough electrons in the core to have it pulled to the surface of the Earth anymore. Too many electrons are leaving the core to have it still maintain a negative potential, which is the magnetism draws everything to the Earth. Everything is magnetically negative in its mass. It's coated with negative particles, and there are always excessive negatives in everything, unless you can drag them out of there with cold. That's when the thing pops up in the air. There's not enough excessive negatives to drag it to the positive Earth, which is always a source of attractiveness for electrons. So, that's gravity too, by the way. Now, where do we go? Ferrite explodes magnets because there's too many electrons. Now we're going to get into my eureka moment. Now, what do I got here? I'm trying to figure out how these things line up. Because, let's take it this way. You know that everything that's in around you is, I'm saying their own regions. So these are all the particles, their own regions. So that's everywhere there is around us. But out in space, they're not like this. They might float around. They're not touching. So they don't bang around. They don't glow. But here, they are touching. Now, how hardly or how much crushing are they doing? Is there any banging them? Is there anybody vibrating them? If there isn't, they get cold. They get colder and colder and colder. You take all of their excess electrons away from them, and they get colder. That's as simple as that. The electrons go to where they are wanted in cold. So if you put excessive cold on something, that will pull those electrons away to warm up that excessive cold you've just put on, like liquid nitrogen. So they pull them out to get them out of there. Pull those electrons faster you can get out. And you see them flowing, just a whole, like cascading of vapors trying to get away from it. And those are loaded with electrons. So that thing becomes basically positive, and it pops up in the air from not being attractive anymore. Now, so there's a whole bunch of things going on like that in the air. But then I got to this about how would these things interact with each other. And I first started going, you put a crystal against a crystal against a crystal, and you got a positive, negative, and you're going to get all this orientation. But then you've got molecules that have all kinds of different orientations. They don't have just the same orientation as this electron. However, I say the nuclear core is electron flooded. I'm starting to think there is no such thing other than electrons. It's the only thing there is. That is my eureka moment. I say actually the entire core of every particle, which is an atom, has a nuclear core, is like a set of bar magnets, a whole batch of them lined up in this orientation. All right, so anyway, what I'm seeing is possibly there is no protons whatsoever, that the cores are made up of these little bipolar electron crystals. That's what I'm going to call them. They're little electron crystals. And they would add together into bar magnets into a resonance frequency that was stable. Now, I've shown this many times about, and you can look it up, vibrating salt resonance frequency experiments, and you'll see they stabilize absolutely flawlessly at a certain resonance frequency, which is the distance of the Venturi, the architecture of the Venturi. And then they just get and then all of a sudden they stop again. Perfectly perfect. Now, that's telling me these resonance frequencies. They are stable only at a certain frequency. And I believe when they get stable, the cores will attract and they'll be stable, and then they won't be stable when there's more of electrons than meets that resonance frequency requirement. And then the next set will be the next element up. That's frequency is stable and good. But in between, you have unstable elements. You might get some that are really close, and you can hang around here for a little while, but we're going to throw you out before long. That's an unstable, that's an isotope. The ones that are exactly fit together like a glove, they're very stable. They won't fall apart and break down easily. The other ones, they're just not stable. They're not in the correct resonance frequencies. That's as far as I can get with it. All right, Mud Fossil University, that's as far as I am with it right now. What I want to know now is about how they change when you shake them and jiggle them, and what's going to, how, in other words, the push will usually come from one side or the other normally. Sometimes you're going to be multi-pushes from all different directions at the same time. That's an explosion. Then there's going to be spin to the right. What I have here, does ether in the air have fabric? Yeah, that's all. Is there ether does the air have a fabric to it? Is it just bumping little things accidentally here and there? I don't know. A lot to consider here. When things move in what direction and other things moving at it in another direction, what is that effect? because everything is coated with electrons, and I'm saying these are electrons. Those are electrons, and they sit on the outside of the core of the nucleus, and I'm now saying the core of the nucleus is nothing more than a pile of these added together until they hit a frequency, a resonance frequency that makes them stable. And that will end up surrounding them. And you can look up tractor beam magnets. Look that one up, tractor beam magnets. And it's Lathamans Toys or something. They got a tractor beam magnet. It's got the core, and the other magnet comes up, boop, and it stops about a half an inch away, and you can jiggle it around and it'll stay there. It won't go away. It stays stuck in that tractor beam magnet spot. Exactly what I'm saying here. The core reaches stability with an excessive bit of negativity, because I believe the negativity overrides the positivity. And so no matter how many there is, it's always going to have an excessive amount of negativity. So you're starting out with every one of the electrons has excessive negativity. So as you add them, it gets more and more and more and more negative. Right? And you collect more and more and more electrons in the outer orbitals. So anyway, that's about as much as I want to go into it now. I'm starting to burn out here. I'm telling you, this gave me a long time to think about this thing. Anyway, that's what we got for today. God bless you, and there's a lot to think about here. I really think I'd like to see some interest from people that you'd expect some interest from, and I'm hoping that'll happen. So talk to other people. Don't be afraid to mention these things. The things I'm talking about aren't silly. All right, thank you. Goodbye.